we figured, or I thought that maybe I would select a few topics that are sort of at the intersection of finance and technology. I mean, maybe I suppose we kind of made a list of things that people care about but don't know much about, and I think on this top of this list was machine learning. Then came fintech, and then cryptocurrencies. So I thought, oh, these were fun topics that we kind of know about but don't, and some of us are. I've heard a lot of people bluffing about these topics. But anyways, so we're happy to have your first lesson, I guess, is that we need a bigger room next time. Partly due to Marcus's reputation, and I'm very happy to have you here. But I'm repeating myself. So this also, I think another reason is that this is a very exciting title, 7 Reasons Most Machine Learning Funds Fail. I want to click on that. And the next one will be, I don't know, everything you've ever wanted to know about fintech, but never dared to ask. And then the last one will be like, oh my God, cryptocurrencies, all the money I could have made. So anyway, look at, we'll keep you informed about our next talks, but since we're all gathered here to see Marco's talk, I would like you to give him a warm welcome.
Thank you, Sasha. Thanks everybody for coming. I'm sure you were curious about the campus rather than the speaker or the topic. Well, now you're stuck here with me. So, I guess everybody has a list of their preferred reasons why competitors go out of business. That's my preferred list. Whenever you hear that a fund is giving back the money or shutting down, you want to do a postmortem to understand what they did wrong so that you are not in the same situation at some point in time. And these are the 7 points I have found over the years to match most of the cases. So let me take them one by one. The first one is what I call Sisyphean quants. What does that mean? Well, suppose that you are a portfolio manager at a discretionary fund, like discretionary macro fund. You are hired to manage money and to take some bets based on ideas that you cannot objectively formulate. If you could objectively formulate, then you wouldn't work in a discretionary fund, you would work in a systematic fund. So essentially you have an intelligent explanation about what is happening in the economy, but it's not something you can actually formulate and explain in an abstract way. Now, the problem with that is that when you have a developed hunch or a little more of something short of a theory, you cannot convey it to your colleagues in an abstract, rigorous way. So that prevents people from having a truly constructive conversation. So when you attend one of these investment committees that occur at the discretionary fund, typically what happens is someone throws some data, another person throws some other anecdotal evidence, but there is not really much of a theory being discussed, something you can experiment and test. And as a result, of course, discretionary funds are very aware of that, so what they do is they allow these PMs to interact, but not much. They should work in silos. And the reason they work in silos is because they are trying to avoid that one PM influence the other, and eventually, I was told that perhaps you should put your mics on mute. With that note, with that mention, I continue. Essentially, the idea is that if one PM influences the other PM, eventually what happens is that you end up paying 50 PNs for the work of one. That wouldn't make sense. So in a discretionary macro fund or discretionary equities fund, any kind of discretionary fund, portfolio managers are asked to work in silos. Does that work in the quant world? Not really. That's one of the reasons I often see quant funds fail. Essentially, the logic of the board of the firm is let's do with quants what has worked with discretionary portfolio managers, and it just doesn't work. You cannot hire 50 PhDs and put them to work together, to work in silos, and everybody is doing 50 times the same thing, collecting the data, 50 different people collecting the data, 50 different people cleaning the data, 50 different people visualizing the data, and 50 people repeating exactly the same tasks over and over and over again. When you ask quantitative portfolio managers to do that, essentially what will happen is typically one of two things. Many of them will frantically look for some investment opportunity or a strategy, backtested in the data. Very often these backtests will lead to a false discovery. They present it to their boss, the investment committee approves, it was an overfitted strategy, it's not going to perform, and eventually what happens is, that there is no strategy and the person gets fired or whatever. So that's very common. Another outcome that you will see very often is many of these 50 PMs will read the literature, read many publications that are in the Journal of Finance and Journal of Financial Economics, so on. Eventually they will settle for some strategy that is based on factor investing. And there is evidence that these strategies actually work, but the reality is, of course, they don't have a Sharpe ratio of 2. They have a Sharpe ratio of 0.5 before transaction cost. So yes, these papers are evidence that there is some profit that you can obtain from factor investing, but it's not what the board is expecting. The board is expecting a Sharpe ratio of 2. So eventually the project is shut down, and you see very often that funds that have been very successful in discretionary portfolio management actually fail when they try to go quantitative. And they go through version 1, 2, 3, 4, 5. They hire a new portfolio manager to lead the quant area, and eventually still they are not able to launch a fund, and they will go through multiple iterations. So that's what I call Sisyphean quants. Sisyphean quants are quants that are asked to roll this massive rock up the mountain all on their own, and guess what? They are very close to the summit, and just when they think that they have found something, it didn't work, and they have to start again. And there is this quote by Albert Camus when he wrote The Myth of Sisyphus. There is no more dreadful punishment than futile and hopeless labor. Isn't it true? Think of it. If you had to go every day to fund, research a strategy, when you have to do it all on your own, without any help, any assistant, you're working in a silo, and you are asked to develop a strategy, and you already know it's not going to work. I'm asked to do the impossible. It's just, at this stage and age, it is impossible for a single individual to, on their own, without any help, identify a strategy that they can develop and implement and run on their own. We are at the stage where the level of competition is such that it may be possible, I mean, like winning the lottery, it's going to be very, very hard. At this point, it requires a team effort. So what does a team effort entail? That's what I call meta strategies. You need a strategy to develop strategies. Strategies cannot be the result of artistic inspiration or some sort of incredible insight. that you realize. Now, you need a strategy to come up with a strategy. Essentially, you need an industrial process. You should be able to produce strategies as BMW produces cars. You need a plan, right? And there are many complexities involved in developing a strategy, right? You need to deal with data problems, with high-performance computing infrastructure, software development, feature analysis, execution simulations, simulators, backtesting, and so on. And the best way to do it is to identify these tasks and divide them and allow everybody in the group to actually specialize in these tasks. So there will be someone who will be the absolute expert in the firm in how to deal with unstructured data. Right? It's on its own. It's such a topic, right? How to deal with unstructured data that on its own actually deserves several people focused just on that. There will be other individuals that are experts in high-performance computing, whether it is distributed computing, or it is a cluster, a supercomputing cluster, or whether it is GPU. There's so many complexities involved in that you actually need people specialized in that. And so on. There will be other people that are experts in TensorFlow, how to develop deep neural networks with specialized software. You cannot ask everyone to be an expert at everything. You're asking too much from people. Now, imagine the situation where you are working in a BMW factory, and you are asked to build the car on your own. Just build the car. On one day you need to be a master welder. Another day you need to be an expert in placing the hydrological system, whatever. I'm not building cars, so I'm making it up. Other days you need to be an expert in the automation of the windows, right? Nobody works like that. Why would any company ask someone to work like that? It's because they don't understand quants. All right. So what would this meta-strategy paradigm do? Every individual is a specialist. They work independently but at the same time knowing the whole game plan. They need to be aware of each other, right? The person who is a specialist in structured data and dealing with unstructured data needs to know how this data is going to be used, needs to be able to answer queries, right? This person will be an expert, for instance, in fixed protocol. Well, it needs to know the analyst who is going to develop a market microstructural strategy that is based on the cancellation rate that is detected in the E-mini S&P. The person who is dealing with the unstructured data needs to know what sort of queries are relevant, what sort of fields in the fixed message need to be stored, how they should be stored, how to handle revisions, corrections to the data. Everyone needs to be aware of each other, but at the same time they need to be specialists. This is not only true for developing strategies, but in fact, you could think of applying meta strategies to everything in the firm. Not only developing strategies, but actually how to hire someone. Right? Hiring someone is a process of sampling. Right? At some point, there is a stopping criterion. At some point, you stop interviewing people and make a decision. What is the optimal stopping point? Now the person has joined the team. How do you oversee the investments? How do you oversee the performance of the strategies? At what point are you going to stop at the strategy? So the meta-strategy paradigm is not only useful for developing strategies, but when you think about it, it's all about how to make decisions under uncertainty, where discovering a strategy is just one of the decisions you need to make, but you actually need to answer many questions about how to manage the quantitative fund. All right. The second problem, integer differentiation. Have you ever wondered why so many papers take as a foregone conclusion that you should differentiate the data? You know, you get some financial data. Of course, the data is non-stationary. Because it is non-stationary, you're not going to be able to do inference, right? You can only do inference on a distribution that is stable over time. So most papers just say, well, let's differentiate the data. Well, what does differentiation do to this data? Because it shouldn't be that you achieve stationarity at any cost. You should figure out what you are paying. When you are differentiating data, you are giving up some information. Are you giving up the most valuable information? As it happens, that's typically the case. When we differentiate data, when we compute returns, for instance, we are erasing the signal. And if we erase the signal, there is no hope we are going to be able to predict anything. So there is a dilemma. On one hand, we have to make the series stationary, but on the other hand, we need to do it in a way that it still allows the series to preserve some memory. Information about previous observations that allows you to discern whether this price or series is at a critical point, at the point where you can actually make a prediction. So this is an example of a fractionally differentiated series of the E-mini SMP. As you can see, the green line indicates, there's your pointer. The green line here shows the series of the E-mini, futures, roll forward. And this is a fractionally differentiated data, where I have differentiated data with a coefficient of 0.4, instead of d equal 1, which is what most people do in the publications, right? They just compute returns. I'm not differentiated by an integer. I'm differentiated by a fraction. So when d is equal to 1, this series will be a series of returns. But as you can see, it's something like a mix of returns and levels, right? When you look at this blue line, at a local point, it looks like returns. But when you look at the whole series, it actually resembles more like the green line, the levels, right? It goes up and down, right up here, around 2008, 2007, and then the big drop, and then recovers. So this happens to be more useful. This is the blue line is a series that is still stationary, so you will be able to run classical analysis and more. Right? The distribution of the blue line happens to be stationary, but at the same time it still contains memory. Meaning that, for instance, here, there is this drop at the end of 2008 because of the crisis, and it takes a while to recover from that drop. It takes perhaps a year, right, or more to recover from that drop, which is something you will not observe in a return series. In a return series, you compute the return of one day and the next can be all the way up. So it's a combination, this blue series, the fractionally differentiated series, or how I call it, something fractive, this fractive series happens to be a combination of the two. Now, let's try to understand a little bit what's going on when you do a fractive of a series. On one hand, if you don't fractionally differentiate the series, if you apply d equal to 0, which essentially means you do nothing, the ADF stat of this series will be minus 0.3387, which means that you cannot reject the hypothesis that there is a unit root. Now, if you apply returns, the ADF is minus 46. So we need a minus 46 to run some analysis that is semi-stationary? No. So it's overdone, right? There's somewhere in between at the point where you are within the threshold that you are willing to accept for a stationarity, but at the same time, the series is still highly correlated with the original series. And that happens around here. Right? You can see here the blue line, which is the ADF stat. The ADF stat touches the critical level of minus 2.86. And what is the correlation of the original series with the fractive series at this point? Is 0.995. What this means is that you have achieved a stationary series, even though the series is essentially you have lost no memory. It's almost perfectly correlated with the original series. So that's what I mean with not giving up too much memory. At this point, the series is almost perfectly correlated with the original one, and yet it's stationary. Compare that with the situation that most people handle, where the correlation with the original series is virtually zero. Right? The standard situation in the literature is returns equal 1. Yes, the ADF is minus 46.9, correlation almost 0. So yes, you achieve the stationarity, but there is nothing to do. The series is useless. Now, is this case of the E-mini unique? Not at all. Actually, there is not a single future, liquid future, where this is not true. Here what I'm showing is a table where for each future contract, I'm using Bloomberg code. Yeah, of course, it's the authority. So here you can see what are, for each future, liquid future worldwide, what is the ADF associated with D equals 0, D 0.1, D 0.2, all the way to returns. And I have plotted in green where the value is above the threshold, and in pink or red, I don't know what this is, when the value drops or falls below the threshold. And as you can see, 0.2 is more or less like the median. 0.2, not 1, 0.2. And not in a single case, I go to the next list, not in a single case you would need D over 0.5. Conclusion, most studies in the literature that try to achieve the stationarity by differentiating, they are over-differentiating by a lot. Because most cases 0.2 would suffice, and yet they apply D equal to 1. Now, yes?
If you were one of the classic PMs you alluded to in the beginning, right? Would you go into this expecting that depending on the asset class, commodity, rates, equities, that you'd have different break-even points? Is it unusual, or would a classicist think it's unusual that it's roughly 0.2, irrespective of the underlying asset class?
Yes, irrespective of the underlying.
Would a classicist PM be surprised by that?
I think so. I was surprised the first time I saw it. I've not seen this published in any paper, so this is breaking news. It's the first time I shared this, and my team probably is mad at me that I'm sharing it, but it's out there now. So the point, these are the 80 most liquid futures worldwide on all asset classes. This includes commodities, FX, futures on fixed income, equities, everything. I've not found a single case where it would be justified to use returns. Let's put it that way. Go ahead.
Just to clarify, D equal to 1 means 1 trading day.
D?
Yeah.
D means one observation, where in this case there are an average of 50 observations per day.
50 observations per day.
But it will be the same on a 50 observations on average. These are volume bars. So some days you may get 10 bars, other days you may get 70 bars. If you use it on daily data, it's even more the case. Meaning that this is already true on intraday data, on higher frequency data. It's already true that you should not, you don't need to compute returns. On daily data is even more the case. Yes, yes.
So it's the bad index.
No, these are volume bars.
Volume bars and work.
On an average of 50 bars per day in the year 2016. So volume bars do not have a regular sampling frequency. Yes, I'll explain. I'll explain in 5 minutes, because this is actually it's on laboratory, I guess, or 4. Many people work with daily bars. God knows why, but you know, it's if you use daily bars, it is even more the case that you do not want to do returns. And the reason is because if you have any chance of predicting a price, it is with intraday data. I mean, daily data is just not granular enough. All right. But you know, it's like I always say in my presentations, try it yourself. I think you will agree that there is nothing special about d equal to 1. I mean, why would d equal to 1 be magic? What is magic about d equal to 1? Why not 0.95? Why not 1.15? Why would everybody use d equal to 1? There is no theorem that proves that d equal to 1 is the optimal differentiation step. Okay, inefficient sampling. So now we're going to discuss volume bars. So most people in the literature, you read that they sample values using daily observations or 1 minute observations or 10 minutes observations. These what I call chronological sampling, right? They're based on a number of bars per day, and it's regular. Why would that be useful? I don't know. I mean, why would you want to sample 10 times per day during the flash crash and 10 times per day on December 31st, one of the most boring sessions in the year? I don't understand it. So what I suggest is that you try and sample based on the amount of information that arrives at the market. So when there is a lot of information arriving at the market, you want to sample more frequently. When there is less information, you sample less frequently. A couple of examples. What I call dollar bars. So what is a dollar bar? It samples whenever there is a certain amount of dollars transacted in the market. So that involves volume and price information. You multiply the amount traded by the price traded, and when it exceeds a certain threshold, which can be arbitrarily chosen, you sample. That means that days with low volume, you receive very little observations, or days where there is little volume and prices are low, because it's much cheaper to transact, there is less money at risk, you would expect that volumes increase, right? So for instance, do you think that there was the same level of market activity before and after the crash of 2008? No. Part of the reason is because after the crash, it was cheaper to buy and sell something. So people who wanted to risk a certain amount of value at risk, people who wanted to risk, let's say, $1 million, they would transact almost double after the crash than before the crash. Well, it sounds like we should take prices into account when we sample information, because definitely, taking 10 observations per year or 10 observations per day, regardless of the volume or the prices, is missing critical information. Well, I don't think we need to go through the exact way these bars are computed. The notion is the important notion here is that you want to take into account price and volume information so that you sample at equal amounts of information that arrive at the market. You want to synchronize your sampling with the amount of information that arrives at the market, so that when there is a lot of information arriving at the market, you want to take more samples. Why? Because they are more useful. They contain more information. All right, 3 examples here: dollar bars, volume bars, and tick bars. So if you sample, for instance, every 10,000 ticks, you would obtain this amount of samples per day. It is a smooth series, but you get that, around 2013, there's a tick. There is the largest number of ticks that you would sample, or tick bars that you would sample per day. What happens when you use volume bars? Well, it's less, the changes are less dramatic, the series is more stable, but still, there is here this sort of like peak and goes down. And when you sample by dollar bars, you obtain a much smoother sampling frequency, where you could link this increase to just the market expanding. There is, you could actually link this to the expansion of the market. Market just grows and there are more participants. But you can see how the black line is very volatile. The green line is less volatile. Dollar bars are much more stable. Why? Because you're sampling closer to the amount to the mechanism that is contributing information to the market. Okay, pitfall number 4. Wrong labeling. So what does that mean? You will read that there are not many machine learning papers in finance, but most of the machine learning papers in finance happen to label in a rather arbitrary way. Essentially what they do is they take a price, and if a price at a given point in time, if, let's say, 10 observations later the price went up, this observation will be labeled as 1. If it goes down, -1. Maybe there is some threshold, and if it within the band as defined by that threshold is labeled as 0. Well, that's kind of arbitrary, right? Because when people label observations that way, they are giving up information about the path. How did the price converge to that outcome? That's one problem. Another problem is that why would you label this feature, this observation, this observed feature, by looking at the next 10 observations? What is magic about 10, right? So that's why I would recommend an alternative way to do this, which is taking into account what happened to the price. How did the price reach a particular outcome? So that's what I call the triple barrier method. Essentially, the way this works is you will start at an initial point, the price goes up and down, and it can touch 3 barriers. An upper horizontal barrier, a lower horizontal barrier, or a vertical barrier. If it touches the upper horizontal barrier, that's what you would call a profit-taking level. If it touches the lower horizontal barrier, that's what you would call the stop-loss level. And if it touches the vertical barrier, that's just like a timeout. You are not willing to hold that position longer. And you label based on the barrier that is touched first. In that way, it doesn't matter what happens after 10 bars. The important is what happened in between. Now, why does that make sense? Well, because whether we like it or not, actually, most people need to follow risk levels, and sometimes we hold a position and we are stopped out either by the risk manager or the investor who wants the money back, or the exchange who comes with a margin call. So it doesn't make sense to develop a strategy that does not take into account these situations where you're forced out of your position. So to be realistic, developing any strategy should take into account stop outs, stop losses, margin calls, etc. Now, there is something called meta-labeling. And what is meta-labeling? Meta-labeling means developing a strategy on top of another machine learning strategy. It's a machine learning strategy that does not try to predict what the price is going to do. It's trying to predict whether the prediction is good. You have a machine learning algorithm that produces a prediction, and the prediction can be something like, buy this stock and hold it for until, either makes 1% or loses 2% up to a maximum of a month. That could be one prediction by the machine learning algorithm. And then on top of that, you develop another machine learning algorithm whose function is to decide whether you're going to ignore that forecast or you're going to implement that forecast. Why is that interesting? Because in that way, you are decomposing the two important decisions into two different models. One model determines the size of the trade, the other model determines the quantity of the trade, where one possible quantity is 0. Meaning that the first model may want to buy a stock, and the second model will say, yes, buy it with but invest in $0, which essentially means pass. I pass on that. Why is this useful? Because if you're familiar with F1 scores, have you heard of? Can you raise your hand if you know what F1 score is? Okay. So an F1 score is a way of combining information about the precision and the recall. So, okay, now I have to say what precision is. Well, precision is the percentage of your predicted positives that actually are positives. So that's the precision. You can have a precision, let's say, of 90%, and you would say, I'm very happy because, whenever I say there is a positive, there's a 90% chance that it's a true positive. Well, wait a moment. How about the recall? And what is the recall? The recall is the percentage of the actual positives that your classifier is identifying. So, for instance, you could have a test that has a 90% precision to detect whether someone is drunk, right? For instance, I don't know. And you would say, well, this test is good. Wait a moment, maybe it's not good because how many of the drunks is the test identifying? We know that when the test says that someone is drunk, there's a 90% chance that this person is actually drunk. But maybe it never says that someone is drunk, or maybe says with 1 out of 1,000. So you need to take both into account, precision and recall, right? And F1 is essentially a harmonic mean of the two. It's a harmonic mean of precision and recall. You could ask, why harmonic mean? Why not an average mean? Well, because actually there is a trade-off between the two. And whenever there is a trade-off between two variables, you rather use a harmonic mean as opposed to an arithmetic mean. For instance, let me give you an example. I guess we all in high school, or in primary school, I don't know, maybe in primary school, we all solve these kind of problems where two trains are about to collide with each other and the teacher is asking you, where are they going to collide and at what time? And the answer is a harmonic mean, right? Because the two trains are advancing one against the other, right? And the same happens here. Typically, it's very hard to achieve high precision and high recall. You may have very high precision, but very likely you will have low recall, or you may have very high recall and low precision. That's why the harmonic mean makes sense. And for the same reason, you want two machine learning algorithms to take care of two very different tasks. One machine learning algorithm will have, the first one, right? Let's say the first level, the first layer machine learning algorithm will have high recall and low precision, and the second one is the one that will filter a lot of the junk produced by the first algorithm and will achieve high precision and high recall. Right? Once you have high recall, even if you have you can have high recall and low precision. That's fine. As long as you have high recall, you still have a chance at having a good strategy. Why? Because the low precision is something you can address. You can just filter a lot of the false positives and achieve high precision without giving too much recall. So that's something that is useful, and in particular should be very useful to funds that are getting into quantamental investing, right? Quantamental investing is this sort of combination of quant investing and fundamental investing. And the idea here is your humans are the first layer machine learner, right? With high recall and low precision. The truth. And then you have the machine learning algorithm sitting on top of them, where they are filtering a lot of the false positives that are pushed by these discretionary traders and achieve high precision with high recall. All right, people number 5, we're almost there. Weighting of non-IID samples. Well, this is a big problem, right? One of the reasons why you cannot find many people from Google starting hedge funds is because, guess what, finance is harder than recognizing faces. Dealing with financial series is not easy. And I like explaining this with the following example. If you work in a lab, like in a, doing, for instance, analyzing blood, you can take one sample per patient, right? You have your sample from this patient, blood sample, in a tube, and now you're going to measure the cholesterol of this person, the amount of whatever, right? Red cells, white cells, insulin, and that's easy, right? Now that's not what happens to us in finance, right? What happens to us in finance is someone collected all the samples and then someone arrived and moved them, and now tube number 10 contains some blood from patient number 10, but also an unknown amount of blood from patient number 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9. And then tube number 1 contains blood from samples from patients 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right? That's what non-IID samples mean. It's a mess. There is no way to link a particular observation to a particular patient. So when you're dealing with non-IID data, you know that there is information about what happened that day, but there is also information about previous samples, and you don't know how much. You need to apply specific techniques to deal with this commingling of the data. Now, this is my dog, Luna. She recognizes faces pretty good. She has no idea about investing. All right? So whenever someone comes to you and says, "Wow, look, I have this machine learning algorithm I developed at Google or Facebook. It recognizes faces. Let's just plug in some financial data." I say, "Look, my dog recognizes faces. Right? My wife claims to be able to drive cars. The jury is still out there whether she actually drives cars." Anyway, dealing with financial data is not easy at all. And one of the reasons is because it's a mess. It's not only dirty data, and not only that financial markets change all the time, right? Or DNA is not changing all the time, right? There is a new regulation, a new law, and things change completely, and exchange changes some way of trading. For instance, they could go from FIFO assignment of a FIFO criterion for placing orders in the queue to a pro rata. And it's just a flip of a switch, as it happened to the 2 years futures a few years ago. And all of a sudden, the data is useless, right? Your data is useless. Now, how can we address this? Well, there are several ways to address the non-uniqueness of the observations. One is to compute the uniqueness of the observation, to derive it. This is one method that I like. Essentially what you do is for every observation, you try to determine the amount of overlap in that observation. So think of the triple variable method, where an observation receives a label as a result of a stochastic process. And essentially what you are asking is how much of the label is the result of information shared with other labels. So for instance, if one observation lasted, the label was decided over observations 1 to 10, and observation 2 was decided over observations 2 to 15, right? They share 2 to 10. 2 to 10 over 2 to 15 for the second one, and 2 to 10 over 1 to 10 for the first one. So the first one is essentially overlap, is essentially a useless observation. The second observation is a little bit more useful. Why? Because it contains information that was not shared in any other label. So once you determine the uniqueness, you can derive how much of the sample weight should be used by the classifier in order to identify a particular pattern. And what you will observe is that sometimes there are observations that are very useful, and sometimes there are observations that are useless. And it makes a big difference to train a classifier with useless data or with useful data. Now, pitfall number 6, cross-validation leakage. Many people think that cross-validation is some sort of magic trick that is going to always tell you the truth, whether this classifier is accurate or not. And the answer is not. Not in finance, anyway. Why? Because cross-validation techniques, and in general, but in particular, k-fold cross-validation, assumes that the observations are IID. Again, that's not true. We wish, but it will never be true. So we have to do something about cross-validation, because if we apply cross-validation to financial series, we are just applying methodology that is assuming that observations are IID when they are not IID. So one thing we can do is we can figure out some way to identify observations that should be removed from the training set. So let's say that you have a tenfold cross-validation, all right? So you know how it works. You split the series in 10, and now you're going to produce 10 training testing splits. In the first one, the first bucket of observations will be the testing set. In the second split, the second bucket of observations will be the testing set, and so on. Now, every time you do a split between training and testing set, you have to figure out what observations in the testing set are leaking information about the training set. Or the other way around. What observations in the training set have leaked information from the testing set. All right. So you want to purge. You want to purge observations in the training set. Do we have the plot of this yet? The plot is the easiest way to say it. Essentially, this is one of the partitions where this is the testing set. And once you have decided what your testing set is, you figure out what portions of the training set need to be removed. Why do they need to be removed? Well, because they contain information that was shared with the testing set. And so there is something that I call purging, right? This would be, for instance, this overlap is the purging. There's an overlap in the information that was used for forming the label. This information needs to be dropped. But in addition, we need to take care of the embargo. We need to do an embargo. Sometimes purging is not enough. Even though you have removed the overlapping information in the training set, in fact, you need to cut deeper, just to be sure, just to be certain, and you need to remove some of the information that occurs after the testing set. Not before the testing set, because before the testing set is fair game, right? We live in a filtration, so we don't care about information that we learned in the past. We care about information that we learn in the future. And that's why the embargo occurs on the right side to the testing set. So to summarize, cross-validation in finance is not that easy. We need to identify observations in the training set that contain information used in the testing set, and that involves two operations, purging and embargo. Now finally, pitfall number 7, backtest overfitting. So I published a bit about this. Maybe you have already read my paper, so I will go quickly. Essentially, the idea is that when you compute a number of backtests, even if the Sharpe ratio of the strategy is 0, just by repeating backtest, eventually you're going to find an amazing strategy on the paper, right? And this is illustrated in this plot, where essentially what I'm plotting is what is the maximum Sharpe ratio that you will identify out of a random Gaussian process with mean 0 and variance, whatever, variance sigma, whatever, variance v. And if you just repeat these backtests 100 times, after 100 times, with the variance 1, the expected Sharpe ratio, the expected maximum Sharpe ratio, the expected maximum Sharpe ratio is around 2.5. So it's very hard not to identify false positives. It's almost impossible. You know, it doesn't matter how well you backtest. You know, you will try to persuade yourself and convince yourself. But I've done everything by the book. I cleaned the data. I didn't look forward. I made sure that all these corporate actions were known at the time I computed. I applied these transaction costs that I found in this paper. Everything was like by the book. And yet the backtest is useless. Why? Because you repeated it 100 times. And it's maddening because, you see, the better you get at backtesting, the less useful it is, right? You know, I backtested for many years. I've been in this business now for 20 years. So, yeah, I know how to backtest. And for me, to identify a strategy in a backtest that looks good is kind of trivial. I'll find someone. I know that I just need to run a few simulations, and everything will be by the book, right? Everything will be, you know, I apply this transaction cost that is recognized in the literature. I clean the data this way, which is recognized in the literature. But the thing is that, you know, if you repeat this 100 times, you are guaranteed an amazing Sharpe ratio for the backtest. So what is the answer? The answer is not to backtest. That wouldn't be smart. You need to backtest. But you need to backtest taking into account the number of trials involved in your discovery. Meaning that the more you backtest, the higher the threshold you should demand for the backtest. So after you have backtested something 100 times, do not be excited when you find a Sharpe ratio of 2. You need to require a Sharpe ratio of, I don't know, 3. And after you have backtested it 1,000 times, do not be excited by a Sharpe ratio of 5. You need to expect a Sharpe ratio of 7, and so on. And there is no horizontal asymptote. So it's not like there is a level at which, I found this strategy with a Sharpe ratio of 10. It has to be true. I mean, it's a Sharpe ratio of 10. No, tell me how many observations, how many trials it took to identify, to make this discovery, because if it is 10,000, probably it's useless. Well, this statistic that I call the deflated Sharpe ratio incorporates a couple of things more. Not only the number of observations, the number of trials involved in your discovery, but also the length of the sample. A practice of 10 years is better than a practice of 1 year. The skewness, the kurtosis, most strategies you find out there happen to have negative skewness and positive excess kurtosis. In fact, most of the hedge funds that you see being launched and raising funds have negative skewness and positive excess kurtosis, and you would wonder why. Why is it that almost all hedge funds out there have negative skewness and positive kurtosis? Well, there is no hedge fund manager that is targeting negative skewness and positive excess kurtosis. But because everybody is being evaluated based on the Sharpe ratio, everybody is trying to maximize the Sharpe ratio. And as it happens, statistically, you can inflate your Sharpe ratio by achieving negative skewness and positive excess kurtosis. So it's kind of funny because nobody's targeting this combination of moments, but because everybody agreed on using any statistic that happens to be inflated, in those circumstances, everybody ended up producing this sort of returns. All right, I'll find out with one example. Suppose that an analyst uncovers a daily strategy with an annualized Sharpe ratio of 2.5 after running 100 independent trials with a variance of half. 1,250 observations, daily observations, so it's like 5 years, with negative skewness, positive excess kurtosis. So this analyst calls you and says, do you want to invest? And your answer is no. Why? Because once you take into account the skewness, kurtosis, sample length, and the number of trials involved in making this discovery, there is only a 90% probability that this reported Sharpe ratio of 2.5 happens to be in reality greater than 0. So there is still a 10% probability that the true Sharpe ratio of this strategy, which is 2.5, that the true Sharpe ratio of this strategy is negative, even though the estimated Sharpe ratio is 2.5. And this plot shows you how the threshold that you must demand for the Sharpe ratio increases with the number of observations, and as a result, how the deflated Sharpe ratio drops very quickly as the number of trials grows. All right, that's all I have to say. Thank you very much. Do you have any questions? Yes. Yes. These assume that these are independent factors. I say yes. Independent. There are ways. Right. So essentially, in the end, you need to have the number of unique factors, independent factors. If your factors happen to be very independent, which is very common, by the way. So very often you see people who practice strategies based on technical indicators, and these technical indicators are not based on any particular theory, so they can be incredibly varied and low correlated. So as it happens, when you practice strategies in the absence of this theory, it's very easy to get the other one. The number of unique factors will grow very quickly because they are actually based on just combinations of parameters. And number two, because the variance of the result will also be very high. Yes? These are the words.
So, when the people are
Yes. Mm-hmm. Yes. So you apply Fractionally to model the data, to make your prediction, right? And once you make your prediction, you can evaluate the outcome of the prediction the way you want with returns, etc. You can still complete the sharp returns. Yes, that the prediction was formed based on data that was fractionally translated. Yes. Yes. So when you say to like applying a backend or panel data,
It was really for your like saving cost professional.
yes.
You're not really like confronted with like computer data. So you're not really how correlation. So like actually.
Yeah. Well, you will still have. Unfortunately, you will still have problems of correlation. It will not be serial correlation, but it's still. Yeah. What I mean, let's make an example. Suppose that you have cross-sectional data for stocks in the S&P 500. Well, very likely the fact that JP Morgan went up means that Goldman Sachs was also up. And so even though there is no serial data, there is no serial correlation because you are forcing the algorithm to work with cross-sectional data, still there will be clusters that mean that the fact that JP Morgan went up is less relevant since Goldman Sachs was also up, and Bank of America, and all those. So still, we will have to deal with non-NIID. Go ahead.
How would you choose the optimal amount of time series data? Because you can choose at a point in time, or very early on, or the whole period, or like 2 years of data in the end, which often fits your model pretty well.
Yeah.
How do you cross-validate that?
So I guess there are two ways to do this. One is to fit your method based on a loopback, and another one is to fit your method based on sample weights that decay exponentially. And in that way, it's not that there is a hard threshold before which every observation is fully used, and then one day or one observation later is entirely dropped. That doesn't really make sense, right? You want to use data that is more recent, and then to have an exponential decay. In that way, now the parameter of choice will be the speed of that decay, but it's not so much whether you should use 100 observations or 101 or 99, which, by the way, would be really bad if once we are in a situation where that makes a difference. It shouldn't make a difference, right? But in any case, it's better to apply sort of exponential smoothing to the data. Yes?
First, in the beginning, you asked about and the later on you argue about non-NIID. Wouldn't doing like non-particle differentiation get rid of this NIID issue? It will be after the full differentiation.
Yeah, look, my personal view is that you do not need to achieve an ADF stat of minus 47%. So the point is not so much to achieve IID observations, because we could apply a differentiation of d equal to 2, and the series would be IID. We have differentiated so much that we not only got rid of all the memory, we even got rid of the zero conditionality of the series. The sweet spot here is to preserve as much memory as you can, and still being able to apply statistical methods. And yes, the implication will be that the series will not be IID, but that's fine because IID or non-IID is two sides of the coin. It's a hassle. You need to. It makes cross-validation very hard. It makes fitting the model very hard, but at the same time, it contains predictive power. Right? That's why, in fact, the goal is never to make the series IID or to make it stationary. You have to make it stationary enough for you to apply these methods and at the same time preserve as much memory as possible. Even if preserving that memory incorporates additional problems like having to apply forging and borrowing of the cross-validation sets, but that's at the same time what allows you to have predictive power.
So this is consider combine the power of Watson and Poker, Hogan, so like over the years, over the previous time, so the it's not they are beating the most smart people, smartest people in the world. Physics complex games. And why they couldn't combine them, or even 10 years from now, why it couldn't be, whatever. Yeah. Well, what's the conceptual we really want to do?
No, I don't think there's a conceptual difference. I think at some point in time we will have machine learning algorithms that definitely will be smarter than any human. Still, someone will have to develop them. At some point in time in the future, we will have machine learning algorithms developing machine learning algorithms, but we are far from that. I agree with you that at some point in time, it's perfectly conceivable that these algorithms will be able to beat humans and beat quants, and but we are far from that. At this point in time, quite frankly, I mean, they recognize faces and they drive cars, but that's. Yeah, this, as you can see, this whole presentation is about how machine learning is not plug and play in finance, and it requires a lot of common sense and experience to figure out why machine learning algorithms fail. Will there be machine learning algorithms that figure out why machine learning algorithms fail and incorporate that in the development? Yes, but we are retired by then. Go ahead.
I do think that the hedge fund is always negative skew and positively focused, and if most traders like to have a larger average win versus average loss, won't they reject that strategy sometimes?
Well, my theory is that it's a result of what is considered an attractive track record, right? The same that when you are breeding dogs, there are some traits that are considered preferable for the shepherd dog, and as a result, these traits are preferred just because some referees prefer them, and over time, yes, that's the breed, right? And it converges into that, and essentially something like that has happened with hedge funds. Everybody liked the Sharpe ratio, and because everybody ended up using the Sharpe ratio, this trait of negative skewness and positive kurtosis, which is very dangerous, it's an explosive combination, happens to be the preferred one. And eventually all hedge funds unknowingly ended up producing this combination even though it wasn't targeted.
So it was just not realized in their sample, the bad.
Right. It's not realized yet. That's exactly the point. It's not realized. But the seeds for their own distraction are there. Right? Because even though there is no fat tail event that has happened, no black swan, they have been selected. They have been selected just like we develop dog races, right? They are selected by our aesthetic preferences, but as it happens, they are ticking bombs. But
I was wondering if you could say something about incorporating correlation into example 3, where you're talking about using dollar and volume bars.
yes,
Right. Because if you're forecasting a bunch of different series in that way, then at some point you would take time.
that's chapter 4 of the book. I address that.
You said something about using recent price data always. Is that your contention, that it's always good to use recent data?
Well, the contention is kind of like that. You think that more recent data is more relevant for the immediate future as opposed to data 100 years ago. The point here is how do you decide the sample length? And my answer was, well, rather than using some arbitrary sample length, let's use all the data just with an exponential decay in the weighting. So you come up with your weighting, with your sample weights, and the observations that are most recent receive more weight than very old observations.
But sometimes events that are very recent are all invalidated by a macro change.
Yes.
So
Yes.
how do you account for that?
Well, that's the basis, right? Essentially, what I'm saying is you fit your classifier with an exponential decay of the weighting, and then you make sure that the backtest is a cross-validation backtest that, for instance, will be fit on very old data, and then see if it can predict the present.
So you titled this "The Reasons Why Funds Fail," machine learning funds fail. Does that mean that if we don't do this, is it the same set of reasons why machine learning funds succeed, or is that different? Or do any machine learning funds succeed?
There is no recipe for success. This is the kind of things I see whenever I hear that a fund blew up. Right? The fund blew up because it was based on a silo model, because people didn't backtest properly, because they didn't take into account that observations are non-NIID, all sorts of reasons, right? Sometimes these reasons are public and they are reported by the press, and sometimes it's like you interview candidates and this candidate comes from this hedge fund that blew up, and you ask this candidate, so what did you do? And they tell you what they do, and you are taking notes of what you shouldn't. So, and after 30 years, this is what I found as the most common reasons. That doesn't mean that this is what you should do and it will work. It has worked for me, but maybe I was lucky.
What's the F score on these 7?
What is it?
What's the F score on these 7?
The F score, the F1 score?
Yeah.
Of what? Of the
Predicting the demise of these funds.
That's a good one. That's a good one. I think it's always a combination of things. It's not like each of these hedge funds that blow up committed 7 sins. Committing one is enough. And sometimes they didn't commit any one, they just were not lucky. But very often you see that, especially the fact that many people backtest without controlling for the number of trials, or they are forced to work in silos. These are very, very common reasons. You get bored to hear those reasons.
You spoke about price and volume, but obviously to be a successful trader, you need to look at many data series besides just that. So
yes.
I'm wondering if a lot of these funds are just hiring statistic people they've never traded before.
Very often.
So that is also something.
Very often. Look, we all have tremendous respect for people that do amazing things in machine learning, Silicon Valley, voice recognition, right? And they do amazing things. But the reality is, finance is different. And for the same reason that you and I would have very little chance at developing a self-driving car, Well, yeah, developing a financial algorithm is hard.
Well, I think we'll end on these wise words, and thanks. I hope that a lot of you